Hello viewers, how are you? Hope you all are fine. So today we are going to discuss torque on a current loop placed in an uniform magnetic field. Let us start. We consider a loop A, B, C, D and A. Current I is flowing through this loop along A to B, B to C, C to D and D to A. This loop is placed in a uniform magnetic field B from left to right in this plane. Now, what will happen to this loop? I mean to say, what is the force on the four sides of this loop AB, BC, CD and DA. So let us calculate this force on the four sides of this loop. Let L be the length and B be the width of this loop. Then area of this loop is A equals to L cross B. Now, what is the direction of this area vector? To find the direction, we take xy plane. This is x and y, and the loop is placed in xy plane. So area vector will be in z direction, that is coming towards your eye, right? We should keep in mind the direction of the area vector. Now this loop is placed in the uniform magnetic field B. So let us first know what is uniform magnetic field. There are lines of forces in any region. We take a cross section there along perpendicular to the lines of forces. Now take a small region in this cross section, and this region contains say one line magnetic lines of force. Now if we rotate this region throughout that loop, and in every region there is number 1 magnetic field, number of lines of forces is 1, then we call this region is in uniform magnetic field. I mean to say, numbers of lines of force per unit area in that region is equal throughout the region. Okay, then this is called uniform magnetic field. So what happens when we place this loop in uniform magnetic field? These four sides will experience force due to this magnetic field, as every side carries current element I. First we calculate force on AD, this line. In this line we calculate force F1. So F1 is the current I times D to A multiply B. This is the amount of the force F1, and this direction DA is along this direction and B is along this direction. DA and B is perpendicular. First case, for the simplest case, we consider DA and B is perpendicular. Then the force will be in upward direction F1. Similarly, for the element BC, B to C, the force F2. F2 is I B to C cross B. And direction of F2 will be in downward direction. and the magnitude of this force F1 and F2 is equal, but the direction is opposite. So this F1 and F2 will cancel each other. So the forces on AD, D2A is F1, and on B2C is F2, and these two forces F1 equals to F2. So these two forces will cancel out each other. Similarly, the forces on side AB is F3, and this force is I A to B cross B, and this will be in this direction, and force on the line C to D will be F4, and this force is I C to D cross B, and this force will be along this direction. As the acting line of these two forces is the same when this loop is placed perpendicular to the magnetic field. Okay, I mean to say the area vector of this loop is perpendicular to B. Then in that case the forces will be equal and opposite, is acting along the same line, and this F3 and F4 will be in opposite direction. Now what happens when we place this loop with an angle theta with the magnetic field B? I mean to say the area vector is an angle theta with a magnetic field B. Then again we will calculate the forces in four sides. First F1 in D2A, then F2 in B2C, okay, then F3 in A to B, and F4 from B to D. So let us calculate this forces on each sides when the loop makes angle theta with the magnetic field, right? Now F1 will be IDA cross B. This F1 will be IDA cross B, and its value will be what? IB B sine 90 plus theta. This theta comes because the area vector makes angle theta with the magnetic field. So this is BIB cos theta, right? So we get F1 BIB cos theta. So we get F1 is BIB cos theta along upward direction. Similarly, we calculate force on B2C, and this value of the force is F2, and F2 will also be BIB cos theta, but with downward direction, right? Again, for this case the forces F1 and F2 will cancel out. Now we investigate the forces on AB and C to D. When this loop makes angle theta with the magnetic field B. In that case, we get F3, that means F3 direction along AB is what? I L B sin theta. Similarly, we get F4 I L B sin theta. In each case, the direction of F3 and F4 should be calculated using Fleming's left hand rule, right? And this F3 and F4, how it will act, their line of acting will not be the same this time. We consider this picture. So the line of acting of these two forces F3 and F4. Here F3 is BIL and F4 is also BIL, the equal magnitude force, and in opposite direction. So these two forces makes a torque on the loop. Now to calculate torque, we will take magnitude, the force, and perpendicular distance between the two forces. So magnitude of the force is B I L and the perpendicular distance is B sin theta. Okay. So what we get? Torque B I L B sin theta. Now this L and B is the area. Okay. So we write tau equals to B I L cross B, we replace it by area A sin theta. Okay. Now if theta is pi by 2, then what will be? B I A. If there are n number of turns in this loop A B C D, then we will multiply with n. Okay. If there is angle theta, then we will put here sin theta. So this is the expression for torque. Now we get tau BIL multiply B sin theta, BIA sin theta. We have replaced L by here A area, and we get tau equals to I A cross B, where A is the area of the loop and B is the magnetic field. If there are n turns in the loop, then we get tau equals to n BIA sin theta. This is the value of the torque which is acting on the loop due to the magnetic field. So I think you have taken note of this. So thank you.